Capacitor, right? Guys, those who are online, are you able to hear me?
Yes, sir.
Good.
Yes, sir.
Projector and sound up. Okay. Maybe not sure if it will work. By any chance, do you guys have mobile in hand? You have? Yeah. Ram Ilya. How many of you have? Okay. Okay. You also don't have a. So can you just log into the device? Link is shared in the group, right? Those who have mobile, can you both share? You don't have, right? You also don't have. Internet. Subrajit, you also don't have a. Guys, just give me a minute. There is a problem here. Put all the volumes at 0. Are you guys able to see? The edge, it has seen many accidents. Please pull it for. You're able to see the screen, right? Okay. So, two things you need to concentrate. For screen content, you have to see the voice, you have to listen to. Okay. So, what was the last topic we discussed? So, the C is equal to Q by V is there, right? So, in the C is equal to Q by V, did I tell you what is the SI unit of it? No, right? Not it. So, if you see, the SI unit here is going to be what? One minute. So SI unit is going to be Coulomb per volt, and this Coulomb per volt is called as FARAD. It is the name of a scientist is called Farad. Okay, and it is written in capital F. One minute. You have mobile? No. You can use this for the time being. Keep it in this room. Any one of you, can you come this side? You have it. It's there. Okay. So listen to this. What were we discussing? So the SI unit is going to be Farad. Okay. Now listen. I have a question here. You are saying C is equal to Q by V, right? So if you are going to change the value of charge, okay, if charge is changed, will there be a change in the value of capacitance? So you're saying C is equal to Q by V. So when you're going to change the charge, is there going to be a change in capacitance? Why? Because Q is changing only because of the value of V. So who is the input here? So V is given as the input and Q is coming as the output. So you've given some voltage and take out some charge. So when this kind of a process is happening, Q and V will change in accordance in such a way that the ratio will always be a constant. Okay, that is why if you see, capacitance of a particular device is always a constant. Are you able to understand? So please make a note of this point. Capacitance of a given device is always a constant and it is independent of the charge or potential difference. And it is independent of the charge or potential difference. Now comes an important question. Then what are the parameters on which it is dependent on? Temperature. So actually it depends on the geometrical parameters. Right? We will see why it depends on geometrical parameters. Shall we start? See, one thing that you need to make a note is you don't have cylindrical and spherical capacitors in your syllabus. You only have parallel plate capacitors in your syllabus. So what did we say a capacitor is? Yesterday we discussed. So what is a capacitor? So if you have two conductors separated by a insulated medium, that is, if they are separated by dielectric, then you call that kind of arrangement as capacitor, right? If there are two conductors in the form of plane sheet, okay, if one is like this and the other is like this, okay, and they are in such a way that the charges to these conductors are given internal, so they are given only inside, right? If this kind of a scenario occurs, then can I say that there is going to be an electric field taking place from the positive to the negative charge? Is it going to take place from the left to the right? Right? And what is the value of this electric field? If I call it as E for the time being. So what is the electric field due to the positive plate? Check your notes and tell me. So we derived it in applications of Gauss law. What is going to be the value of electric field due to positive? Sigma by 2 epsilon naught, right? Sigma by 2 epsilon naught to the right. And what is going to be the value of electric field due to the negative plate? That is also sigma by 2 epsilon naught, right? So both are going to be in the same direction. As a result of it, they'll get added, accepted, right? So sigma divided by 2 epsilon naught plus sigma divided by 2 epsilon naught is equal to the electric field between the plates of capacitor. So this is going to be the value of electric field between the plates of capacitor. Correct? Now, there is a relation between electric field potential difference and distance. So if I say the distance of separation between the plates is D, okay, and the area of cross section of each plate is A. What did I tell you? Distance of separation between the plates is D and the area of cross section is A, right? Then we know the relation E is equal to minus dV divided by dr. What does this tell us? You know this relation E is equal to minus dV by dr. Am I clear with this? Right? What does this relation tell us? Electric field is in the direction of decreasing potential, but you use that minus dV by dr only when there is going to be a larger variation that is going to occur. Now, if you take a capacitor, right, and you connect it across a potential source, if you see a capacitor in real time, it will be very, very, very small. Okay, a capacitor in general will be this small. It looks something like this. It is really this small. Okay, so if you take this kind of a device, I can say that the potential difference is almost a constant, right? Then I can say E is equal to V divided by D. So this is the value of relation between electric field and V. Okay, so E is equal to V divided by D. Any doubt on this? So what will be the value of electric field between the plates? It is sigma by epsilon naught. I'll call that as equation number 1. And E is equal to V by D. I'll call it as equation number 2. Correct? Now see. From 1 and 2, can I say sigma by epsilon naught is equal to V divided by D? Can I say sigma by epsilon naught is V by D? Right? But what is sigma, guys? How do you define? Q by A. So Q divided by A into epsilon naught, can I write it as V divided by D? Sanjeevan, you are able to understand? Yeah. So if I rearrange this equation, then I'll get Q by V is equal to epsilon naught A into A divided by D. Epsilon naught into A divided by D. Accepted? Correct? So, but what is this Q by V? This is what is the capacitance. So, if you see the capacitance of a parallel plate capacitor, it is going to be equal to epsilon naught A divided by. Am I clear, guys? So, this is the whole derivation. Please make a note of it. Those who couldn't write it, please look at your phones and then write. Is this clear or this one is better? This is better, huh? Okay. Right. So it is epsilon naught A divided by D. So from this we can understand what are all the parameters on which the capacitance depends on. Yes, it depends on the distance of separation. It depends on the area of cross section, and it depends on the permittivity of the medium in between. So if you see in this case, we use the air itself as a medium, right? So this is called permittivity of, I can write it as medium itself, medium that is there between the plates of the capacitor. Am I clear with this, guys? Right. Now, shall I move on to the next topic? So what is the heading? This is the capacitance of a, this is the capacitance of whom? This is the capacitance of a parallel plate capacitor. Please write down the heading there. So if they ask you the derivation, right? These are the steps that you need to follow. Capacitance of a parallel plate capacitor. Okay. Next is, there is a term called as dielectric strength. Okay. So observe, when you are taking a capacitor, right, the intermediate medium is going to be dielectric. Right? In general, it is going to be dielectric. But by you taking those two plates, what are you creating between them? You are creating some electric field between the plates of the capacitor. And where is that electric field passing through? The electric field itself is passing through dielectric. Now, what can happen? So, yesterday we discussed a concept called as polarization. You remember that? So, inside a dielectric, you have dipoles, and those dipoles will get aligned in such a way that left end will be. So, when you take the electric field from left to right, the left end of the dipole will get more of negative charge, and the right end will get positive charge, and there is an induced electric field acting from right to left. You guys remember this, right? So, having this point in mind, can I say, as you keep increasing the value of electric field, what are you doing? You're keeping on increasing the value of electric field. If you're increasing it between the plates of the capacitor, what do you think will happen to the dielectric? Will it be able to withstand a longer value? Longer means you keep increasing longer magnitude of the electric field. You keep increasing the value of electric field. Do you think the dielectric will exist forever by taking in how much ever electric field you keep giving in? There is a threshold for every material in this world, right? Means there will be a breaking point, right? So there is a point called as dielectric strength. So name itself is suggesting. Dielectric strength means the strength of the dielectric. To do what? To withstand the maximum value of electric field. Okay. So make a note. The maximum electric field that a dielectric medium can, what is the page number? No? Page number 74 in your textbook, there is a line. So the maximum electric field that a dielectric medium can withstand without breakdown. The maximum electric field that a dielectric medium can withstand without breakdown is called dielectric strength. So here, if you see, we are using the word without breakdown. What does it mean? What do we mean by without breakdown? Breakdown means literally, is it going to break into pieces? No. In the bracket, something is given C. Its insulating property means as you keep increasing the value of electric field, there will be one particular point at which this insulator, that is the dielectric, will get converted into a conductor. Means it will break down, it will lose all its insulating property and suddenly start conducting. So that is the point at which it has lost its dielectric properties. And that value of electric field which is able to create this property in the dielectric is what is called as dielectric strength. So what is dielectric strength? It is the value of electric field. So it is the value of the maximum electric field that you can give so that it does not lose its property. Is what is called as dielectric strength. Have this in your mind. Okay. So about the parallel plate capacitor, I've already explained the capacitance, right? Now, so you are able to see this. C is equal to epsilon naught A divided by D. This thing we have already derived, right? So these two concepts are over. Any doubt from here? You're clear till this point? Okay. Now the next question is, so in the previous derivation, what did we do? We kept a conducting medium, that is air, in between the plates of the capacitor, right? Now the question is, what if that dielectric medium is replaced with something else, which has a different, I would call it as different permittivity. Okay, let's see how it works. So the next heading that you need to write is effect of dielectric on capacitance. So write on the heading. Effect of dielectric on capacitance. Now you guys tell me, will there be a change in the value of capacitance or not? There will be, right? What do you think will happen to the capacitance? Will it increase or decrease? So initially you have air medium. Okay, let's say the capacitance is C0. Now you insert a dielectric between the plates of the capacitor. Do you think its capacitance is going to increase or decrease? It will increase, but you're putting an insulator in between. Okay. Think about it and answer. I'll repeat the question. Listen. Initially, when you took the derivation, when you got epsilon naught A divided by D, I'm able to understand that between the two parallel plates, I have air medium present. Correct? So now you're replacing that air medium with a dielectric. Dielectric is an insulator. When you insert it, so initially, let's say the capacitance is C0. When was it? When was it C0? When the air medium was present. Now let's say the capacitance is C dash. What will be the relation between C0 and C dash? Is C0 going to be greater than C dash or C0 will be less than C dash? Is what my question is. C0 will be greater than C dash. That's what we expect, right? Why is it so? Because but you're trying to put in what? Dielectric. That is why you think the capacitance will decrease. Is that right? Actually, that is wrong. The capacitance after putting a dielectric should increase. Why? Yesterday I gave you the logic for it. I told you about an aluminum sheet. You remember? You take an aluminum sheet, you give charge to it. Can you hold that charge for a longer duration? So you have an aluminum sheet and a paper in your hand. Which one will hold the charge for longer duration? It is a paper, right? In a similar way, what is the work of a capacitor? To hold charge. It is not to conduct the charge. Its property is to hold the charge. If that has to stay for a longer duration, what kind of a material is needed? You need a dielectric. That is the reason why dielectric plays an important role in the case of capacitors. It's not the case. It's not in the case of conductors. So are you able to understand the difference between both? What does a conductor do? Conductor is a material which can conduct electricity, allow the flow of charges. Whereas dielectric, why is it helping in this case? Though it is treated as a negative term, non-conducting. Why is it useful here? Because it does not leak the charges to the surroundings. It helps to hold the charge. Relative permittivity into C0. That we have to derive and see. No? We have not yet touched it. Okay. So I'll give you a minute time. Yesterday, I taught you the concept of dielectrics, right, and polarization. There, look at the value of electric field that I gave you. Revisit your notes. Revisit the topic in your notes. When you spoke about a conductor, what was the net electric field inside? 0. But whereas when you spoke about an insulator, what was the net electric field inside? E0 minus E induced was equal to something. What was it? E naught divided by K. What K is actually kappa. What is that kappa? It's called relative permittivity or dielectric constant. Are you able to understand? So that is a very, very, very important expression which we are going to use now. Shall we get started? Right. So did you all write down the heading? Effect of dielectric on capacitance. So when you say the electric field due to the charges on plates of the capacitor is E naught. What is the value of E naught? E naught is equal to sigma by epsilon naught. Accepted. Right. What will be the electric field inside the capacitor? What will be the value of electric field inside the capacitor according to the concept from yesterday's discussion? It should be E naught by kappa, right? So electric field inside, it is not induced. Electric field inside should be equal to sigma divided by kappa into epsilon naught. Can I call this as equation number 1? Right? So if you look at the previous derivation, what were the steps that we followed? We first wrote down the expression for electric field. Then we wrote the relation between electric field and potential difference. So if I say E is equal to V divided by D, here what is going to be the value of electric field inside? So I will write electric field inside is V divided by D. So sigma divided by kappa into epsilon naught is equal to V divided by D. Accepted? Right. Now what is going to happen with respect to sigma? I can write it as Q divided by A into epsilon naught is V by D. Now rearrange the equation and tell me. Rearrange the equation so that you have Q by V on left hand side is equal to what will you have on the right hand side? Kappa epsilon naught A divided by D. But what is that Q by V, guys? Capacitance. And you have this kappa into epsilon naught A divided by D, right? What is that epsilon naught A divided by D? That was the initial value of capacitance before inserting the dielectric. Are you guys able to understand? So that value is C naught. So final capacitance C dash is equal to kappa times C naught. This is the important observation that we need to make. Guys, am I clear with this? Is there anyone having doubt on this? So did you understand these steps? So whenever you are asked to calculate the capacitance, what is the first step you need to do? First is, if you see the flow, what is that you have written in your notes? Check. The first step is define electric field. Second step is define the relation between electric field and potential difference. Third step is rearrange the equation and you will get the value of capacitance. These are the 3 steps you need to follow. You can do that. Is that clear, guys? Okay. So here I want you all to make an important note. Here, what is the thickness of dielectric? The thickness of dielectric in this scenario is D. Okay. First, write down this one. Then I'll tell you about the next one. Thickness of dielectric, how thick the dielectric is, means how much space between the plates is it occupying. So if the distance between the plates is D, then you have taken a dielectric and completely placed in that space D. That is the meaning. No, there is no space. Okay. So having this in mind, I want to explain the next concept. See, but before that, if you have to know the symbol of a parallel plate capacitor, you draw two lines and you put like this. One can be positive and the negative. So it is something similar to a battery where both the lines are of equal length. Okay. This is called capacitor of fixed capacitance. So what do we mean by fixed capacitance? Capacitance is constant. Means if you buy a capacitor, its value is always a constant. Suppose you have a line like this. Okay, then this is called as variable capacitor. So what do we call it as? Variable capacitor. In the sense, you can change the value of the capacitor as you perform the experiment. It is something similar to a rheostat. Okay, where you call that as a variable resistor. Here you call it as a variable capacitor. Am I clear, guys? Regulator is variable resistance. Regulator uses the principle of variable resistance, not capacitance. Okay. Where? Okay. Because E is equal to V by dr. Right. The electric field inside is what? Is it not E naught divided by kappa? This is equal to V divided by dr. But what is E naught? Sigma by epsilon naught. So sigma by epsilon naught into kappa is equal to V divided by d. But what is sigma? Q by A. So Q divided by A epsilon naught into kappa is equal to V divided by d. Want me to go back to the previous step? Previous slide. Yeah. Yeah. So if anybody wants to make a note, please make a note. Talking to the net electric field, I'm not talking to individual electric fields. Understood? Done, guys? Yeah, shall we move to the next one? Listen, this is a slightly critical, I'll not say critical, you need to focus. So, effect of dielectric on capacitor. When a dielectric of thickness T is inserted between the plates, where T is less than D. So I repeated, effect of dielectric on capacitor when a dielectric of thickness T is inserted between the plates where T is less than D. Write down this, write this as the heading. Okay. Now see, if you look at the diagram, it is going to be in this way. You have two plates between which you have inserted a dielectric of thickness T. Okay. And the distance between the plates of the capacitor is D. Is that clear? Then how much is the outside medium? D minus T. Is that clear? Now, if I apply a total potential difference of V volts across the ends of this capacitor, how much am I applying? I'm applying V volts across the ends of this capacitor. Can I say V1 volt is occupied or taken by the dielectric, and the remaining V2 volt is taken in the air medium? Are they not looking like they're in series? Yes. So when that is the case, can I say V1 plus V2 is equal to V? Yes or no? So V1 plus V2 is equal to V in the sense, what is V1, guys? Listen. So the net electric field outside is going to be E naught. The net electric field outside is E naught. Then in this space, how much is going to be the electric field? Tell me. E naught by, this is a dielectric. So inside the dielectric, see, if outside electric field is E naught, what will be the electric field inside? E naught divided by kappa. And here it is still E naught. Accepted? Right. So can I say E naught divided by kappa is equal to V1 divided by T? Observe this expression. E naught divided by kappa is equal to V1 divided by T. Is that right? Correct? Then what about E naught? E naught will be V2 divided by D minus T. Accepted? Which implies V1 is equal to E naught divided by, V1 is equal to E naught divided by kappa into T, and V2 is equal to E naught into D minus T. Observe it. I'll give you some time. Is that clear? So V1 is equal to E naught by kappa into T, V2 is equal to E naught into D minus T. But what is V equal to, guys? V1 plus V2. Okay. So V1 plus V2 now, it is going to be E naught by kappa into T plus E naught into D minus T. Okay. Now, if I rearrange this equation, what am I going to get? E naught into D plus E naught divided by kappa into T minus E naught into T. So if I take this out, E naught D plus E naught T into 1 by kappa minus 1. Or I can write it as E naught into T by kappa minus T. Is there any doubt in this? Just keep writing along with it. I just wanted E naught because I'll write that E naught as sigma by epsilon. Okay. See, generally, if you see this expression is written like this, E naught into D minus T plus T divided by kappa. This is the most famous way of writing it. So E naught into D minus T plus T divided by kappa. If I call this as V, then what is E naught, guys? What is E naught? V naught is sigma by epsilon naught. E naught is sigma by epsilon naught into D minus T plus T by kappa. இப்போ என்ன பண்ணலாம்? Sigma, when what can I write it as? Q divided by A into epsilon naught into D minus T plus T divided by kappa. Right? Now rearranging the equation, Q by V will be equal to epsilon naught A divided by D minus T plus T divided by kappa, and this is going to be the new capacitance. I'll call it as C double dash. Okay. So what are the capacitance? When you insert a dielectric with thickness T, this is the formula. Epsilon naught A divided by D minus T plus T by kappa. So there is the value. Okay. Now the important question is, if T is equal to D, what would have happened? If T is equal to D, take this and substitute in this expression and tell me what is the value. Correct. So is that not the expression we got in the previous case? Right. So this is what you will get. Now the question is, you can make a note. If there are n dielectrics of thickness T1, T2, so on till Tn, and dielectric constants kappa 1, kappa 2, so on till kappa n, then the capacitance will be equal to, can someone guess? Look at the above expression, epsilon naught A divided by D is D only. D minus, so I'm looking at this expression, D minus, what will you get? T1 plus T1 by kappa 1 minus T2 plus T2 by kappa 2. It keeps on going. Last one will be minus Tn plus Tn divided by kappa n. All these things in the denominator. Okay. Okay. Clear. So based on this, can we try out one problem from textbook? Yes. Let me know if you guys are done. Is everyone done? Okay. Yes. So now we'll try out this problem 2.8. So you already have the formula. Only thing is read the question properly, take the data and solve it. So problem 2.8. There is a slab of material of dielectric constant kappa that has the same area as the plates of a parallel plate capacitor, but has a thickness of 3 by 4 times D. Okay, where D is the separation of the plates. How is the capacitance changed when the slab is inserted between the plates? Did anyone get the answer? Simplified. Simplified. I don't know what is the answer. Simplified. So what are you able to understand? So there is a dielectric constant. There is a material of dielectric constant K has the same area as that of the parallel plate capacitor, but has a thickness of 3 by 4 D, where D is the separation between the plates. How is the capacitance changed? So initially, if I call the capacitance as C naught, finally let me call the capacitance as C. What is the formula? Epsilon naught A divided by D minus T plus T by kappa. So it is going to be epsilon naught A divided by D minus D minus 3 by 4D plus 3 by 4 D by kappa. Correct? So this will be how much? Epsilon naught A divided by D minus 3/4 of D is D by 4 plus 3D by 4 kappa. So what is the LCM? I can multiply with kappa here and here. So I will take that 4K to the numerator, 4 times kappa into epsilon naught A divided by kappa times D plus 3D. Okay, this is the value. But this I can write it as 4 times kappa into divided by D plus 3 into epsilon naught A divided by D. Sorry. 4K divided by kappa plus 3 into epsilon naught A divided by D. They both are same. But what is epsilon naught A divided by D? That is what is C naught. So how is the capacitance going to change? It will increase by a factor of 4 times kappa divided by kappa plus 3. That's the answer. Mm-hmm. 4 kappa divided by K plus 3. Any doubt? Scroll up. Okay. Guys, those who are online, any doubt?
No, sir. No doubt, sir.
Okay. Right. So the next few concepts that are left out are combination of capacitor, that is capacitors in series and parallel. Then we have what is the energy stored in a capacitor. With that, we are done with this chapter. Okay. See, I'll be stopping with this for today. Okay. Next class will complete it. I'll try to work on this projector also. Any other doubts from today's class? Clear, right? You guys could make note. Guys, those who are online, any doubts?
No, sir.
Okay. So if no more doubts, we can wind up.
Thank you, sir.
Yeah.